mechanics, the Robertson-Schrödinger relation follows from a positivity condition on a real star square function given a Wigner function W x p with start product star and a function f. The following is generally to f** star f equals integral f asterisk star f w x p dx dp greater equals 0. Choosing f equals a plus bx plus cp, we arrive at f asterisk star f equals a asterisk b asterisk c asterisk 1 xp x star x star p star x p star p a p c greater equals 0. Since this positivity condition is true for all a, b, and c, it follows that all the eigenvalues of the matrix are non-negative. The non-negative eigenvalues then imply a corresponding non-negativity condition on the determinant and 1 xp x star x star p star x p star p equals determined 1 xp x squared xp plus ih divided by 2p xp minus ih divided by 2p squared greater equals 0, or explicitly after algebraic manipulation sigma 2x sigma 2p equals x squared minus x squared p squared minus p squared divided greater equal xp minus xp squared blah 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 xp parentheses blah plus h squared divided by 4. Examples of the Robertson and Schrödinger relations are for general operators. The relations can be applied to any two observables to obtain specific uncertainty relations. A few of the most common relations found in the literature are given below. Position, linear momentum, uncertainty relation for the position and linear momentum operators. The canonical commutation relation x hat check b hat check equals I H implies the canonical equality from above. Sigma x sigma p greater equal h divided by 2. Angular momentum uncertainty relation for two orthogonal components of a total angular momentum operator of an object. Sigma j e sigma j greater equal h divided by 2 jk, where ijk are distinct and gi denotes angular momentum along the x-axis. This relation implies that unless all three components vanish together, only a single component of a system's angular momentum can be defined with arbitrary precision. Normally, the component relative to an external magnetic or electric field. Moreover, for gxgy equals IH epsilon xyz jz, a choice a hat check equals jx, b hat check equals jy, an angular momentum of multiplied g equals jm bounds the Casimir invariant. Angular momentum squared j2x plus j2y plus j2z from below, and thus yields useful constraints such as j parentheses open j plus 1 parentheses closed greater equal m parentheses open m plus 1 parentheses closed, and hence j is greater equal m among others. For the number of electrons in a superconductor and the phase of its for the number of electrons in a superconductor and the phase of its Ginzburg-Landau order parameter of a number of electrons in a superconductor and the phase of its Ginzburg-Landau order parameter delta in delta phi greater equal 1. Limitation for derivation of the Robertson inequality for operators a hat check and b hat check requires a hat check b hat check g and b hat check a hat check g to be defined. There are quantum systems where these conditions are not valid. One example is a quantum particle on a wing where the wave function depends on an angular variable theta in the interval 0 to p. Define position and momentum operators a hat check and b hat check by a hat check phi theta equals theta g theta as an element of set 0 to p, and b hat check g equals minus I h dg divided by d theta with periodic boundary conditions on b hat check. The definition of a hat check depends the theta range from 0 to 2p. These operators satisfy the usual commutation relations for position and momentum operators a hat check b hat check equals I h, more precisely a hat check b hat check g minus b hat check a hat check g equals I h g whenever both a hat check b hat check g and check, B hat check, A hat check, G are defined in the space of such G is the dense subspace of a quantum Hilbert space. Now let G be any of the eigenstate of B hat check. We are given by phi theta equals e to the power of 2 p e n theta. These states are normalizable, unlike the eigenstate of a momentum operator on the line. Also, the operator A hat check is bounded since theta ranges over a bounded interval. Thus, in the state phi, the uncertainty of B is 0 and the uncertainty of A is finite, so that sigma A, sigma B equals 0. The Robertson uncertainty principle does not apply in this case. G is not in the domain of the operator B hat check, A hat check, since the multiplication by theta disrupts the periodic boundary conditions imposed on B hat check. For the usual position on momentum operators X hat check and B hat check on the real line, no such counterexamples can occur. As long as sigma x and sigma p are defined in the state G, the Heisenberg uncertainty principle holds even if G fails to be in the domain of X hat check, B hat check, or of P hat check, X hat check. Mixed states. The Robertson-Schrödinger uncertainty can be improved, noting that it must hold for all components Quachi K in any decomposition of the density matrix given as Quachi equals sum K pk Quachi K. Here the probabilities pk greater equals 0 and sum K pk equals 1 hold when using the relation sigma. Ja, oder halt sum K AK sum K BK greater equals sum K root AK BK to the power of 2 squared. For AK BK greater equals 0, it follows that sigma 2A sigma 2B greater equals sum K PKL Quachi K squared when the function in the bound is defined as Quachi equals root a half heißt wahrscheinlich Trigonometrie? Nee. Tangente. Senkante. Aber was heißt Rho A B minus Rho A Rho B squared root half Rho AB minus Rho A root half Rho AB minus Rho A Rho B squared plus 1 divided by 2I Rho AB squared. The above relation very often has a bound larger than that of the original Robertson-Schrödinger uncertainty relation. Thus, we need to calculate the bound of a Robertson-Schrödinger uncertainty for the mixed components of a quantum state rather than for the quantum state and compute an average of a square root. The following expression is stronger than the Robertson-Schrödinger uncertainty relation. Sigma 2a, sigma 2b greater equal max pk Quachi k sum k pkl Quachi k squared, where on the right hand side there is a concave roof over the decompositions of a density matrix. The improved relation above is saturated by all single qubit quantum states. Where on the right hand side there is a concave where sigma 2, sigma 2a, sigma 2b greater equal max pk Quachi k sum k pkl Quachi k squared. Where on the right hand side there is a concave roof over the decompositions of a density matrix. The improved relation above is saturated by all single qubit quantum states. With similar arguments, one can derive a relation with a convex roof on the right hand side. Sigma 2a f q Quachi b greater equal 4 min pk, also minimum min pk gk sum k pkl gk squared, where fq Quachi b denotes the quantum Fisher information and the density matrix is this decomposite, where fq Quachi b denotes the quantum Fisher information and the density matrix is decomposed to pure states as Quachi equals sum k pk gk. The derivation takes advantage of the fact that the quantum Fisher information is the convex roof of the variance times 4. A simpler inequality follows without a convex roof. Sigma 2a fq Quachi b greater equal iab squared, which is stronger than the Heisenberg uncertainty relation, since for the quantum Fisher information we have fq Quachi b smaller equal for sigma b, while for pure states the equality holds. The Macon-Patty uncertainty relations, the Robertson-Schrödinger uncertainty relation can be trivial if the state of a system is chosen to be eigenstate of one of the observable. The stronger uncertainty relations proved by Lorenzo Macon and Arun K. Patty give non-trivial bounds on the sum of the variances for two incompatible observables. The stronger uncertainty relations proved by Lorenzo Macon and Arun K. Patty give non-trivial bounds on the sum of the variances for two incompatible observables. The stronger uncertainty relations proved by Lorenzo Macon and Arun K. Patty give non-trivial bounds on the sum of variances for two incompatible observables. Earlier works on uncertainty relations formulated as the sum of variances include e.g. Exempli gratia ref due to Xichen Huang. Earlier works on uncertainty relation formulated as the sum of variances include exempli gratia reference due to Xichen Huang. For two non-commuting observables A and B, the first stronger uncertainty relation is given by sigma 2a sigma plus is given by for two non-commuting observables A and B, the first stronger uncertainty relation is given by sigma 2a plus sigma 2b greater equal plus minus I g a b g plus g a plus minus I b, where sigma 2a equals g a squared g minus g a g squared, sigma 2b equals gb squared g minus gb g squared. G is a normalized vector that is orthogonal to the state of a system G, and one should choose a sign of plus minus I g a b g to make this real quantity a positive number. The second stronger uncertainty relation is given by sigma 2a plus sigma 2b greater equal half g a plus b g squared, where g a plus b is a state orthogonal to G. The form of g a plus b implies that the right hand side of a new uncertainty relation is non-zero unless G is an eigenstate of a plus b. One may note that G can be an eigenstate of a plus b without being an eigenstate of either a or b. However, when G is an eigenstate of one of the two observables, the Heisenberg-Schrödinger uncertainty relation becomes trivial, but the lower bound of the new relation is non-zero unless G is an eigenstate of both. Implies that the right-hand side of a new uncertainty relation is non-zero unless G is an eigenstate of a plus b. One may note that G can be an eigenstate of a plus b without being an eigenstate of either a or b. However, when G is an eigenstate of one of the two observables, the Heisenberg-Schrödinger uncertainty relation becomes trivial, but the lower bound of the new relation. One may note that G can be an eigenstate of a plus b without being an eigenstate of either a or b. However, when G is an eigenstate of one of the two observables, the Heisenberg-Schrödinger uncertainty relation becomes trivial, but the lower bound in the new relation is non-zero unless G is an eigenstate of both. Energy time. An energy time uncertainty relation like delta E, delta T greater tilde H divided by 2 has a long controversial history. The meaning of delta T and delta E varies, and different formulations have different arenas of validity. However, one well-known application is both well-established and experimentally verified. The connection between the lifetime of a resonance state, R, root 1 divided by 2, and its energy with delta E. R root 1 divided by 2 delta E equals pH divided by 4. In particular, physics rifts from experimental fits to the Breit-Wigner energy distribution are used to characterize the lifetime of quasi-stable or decaying states. An informal heuristic meaning of the principle is the following: a state that only exists for a short time cannot have a definite energy. To have a definite energy, the frequency of a state must be defined accurately, and this requires the state to hang around for many cycles. The reciprocal of a required accuracy. For example, in spectroscopy, excited states have a finite lifetime, but the time energy uncertainty principle, they do not have a definite energy, and each time they decay, the energy they release is slightly different. The average energy of the outgoing photon has a peak at the theoretical energy of the state, but the distribution has a finite width called the natural line width. Fast decaying states have a broad line width, while slow decaying states have a narrow line width. The same line width effect also makes it difficult to specify the rest mass of unstable, fast decaying particles in particle physics. The faster the particle decays, the shorter its lifetime, the less certain is its mass, the larger the particle's width. Fast decaying states have a but the distribution has a finite width called the natural line width. Fast decaying states have a broad line width, while slow decaying states have a narrow line width. The same line width effect also makes it difficult to specify the rest mass of unstable, fast decaying particles in particle physics. The faster the particle decays, the shorter its lifetime, the less certain its mass, the larger the particles. We have time and quantum mechanics. The concept of time and quantum mechanics offers many challenges. There is no quantum theory of time measurement. Relativity is both fundamental to time and difficult to include in quantum mechanics. While position and momentum are associated with single particle, time is a system property. It has no operator needed for the Robertson-Schrödinger relation. The mathematical treatment of stable and unstable quantum systems differ. These factors combine to make energy, time, and uncertainty principles controversial. The three notations of time can be distinguished. External, intrinsic, and observable. External or laboratory time is seen by the experimenter. Intrinsic time is inferred by changes in dynamic variables like the hands of a clock or the motion of a free particle. Observable time concerns time as an observable measurement of time-separated events. An external time, energy, time, uncertainty principle might say that measuring the energy of a quantum system to an accuracy delta E requires a time interval delta T greater than h divided by delta E. However, Runoff and David Bohm have shown that in some quantum systems, energy can be measured accurately within an arbitrarily short time. External time uncertainty principles are not universal. However, Yakir Aharonov and David Bohm have shown that in some quantum systems, energy can be measured accurately within an arbitrarily short time. External time uncertainty principles are not universal. Intrinsic time is the basis for several formulations of energy-time uncertainty relations, including the Mandelstam relation discussed in the next section. Physical system with an intrinsic time closely matching the external laboratory time is called a clock. Intrinsic time is the basic for several formulations of energy-time uncertainty relations, including the Mandelstam relations. Mandelstam relation discussed in the next section. A physical system with an intrinsic time closely matching the external laboratory time is called a clock. Observable time measuring time between two events remains a challenge for quantum theories. Some progress has been made using positive operator value measure concepts. Mandelstam in 1945. Leonard Mandelstam and Igor Tam derived the non-relativistic time-energy uncertainty relation as follows. From Heisenberg mechanics, the generalized Ehrenfest theorem for an observable B with an explicit time dependence represented by a self-adjoint operator B relates time dependence of the average value of self-adjoint operator B hat check. Relates time dependence of the average value of B hat check to the average of its commutator with a Hamiltonian D B hat check divided by dt equals I divided by h. A hat check, B hat check. The values of A hat check, B hat check is when substituted in the Robertson uncertainty relation for the energy operator A hat check and B hat check. Sigma h, sigma b greater or equal 1 divided by 2I A hat check, B hat check, giving sigma h, sigma b divided by d, b hat check divided by dt greater or equal h divided by 2 whenever the denominator is non-zero, while this is a universal result, depends upon the observable chosen and that is the differential, the deviations sigma h and sigma b are computed for a particular state, and identifying delta E is identical to sigma E, and the characteristic time dB identical sigma B divided by D B hat check divided by dt gives an energy time relation delta ETB greater or equal h divided by 2. Although TB has the dimension of a time, it is different from the time parameter t that enters the Schrödinger equation. This TB can be interpreted as time for which the expectation value of an observable B hat check changes by an amount equal to 1 standard deviation. Examples: the time a free quantum particle passes a point in space is more uncertain as the energy of a state is more precisely controlled. Delta T equals h divided by 2 delta E, so the time spread is related to the particle position. The spread and the energy spread is related to the momentum spread. This relation is directly related to position momentum uncertainty. A delta particle is a delta particle across a stable composite. A delta particle across a stable. A delta particle a quasi-stable equivalent. A delta particle a quasi-stable composite of quarks related to protons and neutrons has a lifetime of 10 to the power of minus 23 seconds. So its measured mass equivalent to energy 1232 mega e v divided by c squared varies by plus minus 120 mega e v divided by c squared. This variation is intrinsic and not caused by measurement errors. Two energy states C1, 2 with energies E1, 2 superimposed to create a composite state. Phi xt equals He1 x e to the power of minus 1. Gxt equals He1 x e to the power of minus I E1 t divided by h plus Bg2 x e to the power of minus I E2d divided by h. The probability amplitude of a state has a time-dependent interference term. Gxt squared equals a squared G1 x squared plus b squared G2 x squared plus 2ab c. The oscillation period varies inversely with an energy difference R equals 2b h divided by E2 minus E1. Each example has a different meaning of a time uncertainty according to the observable and state used. Quantum field theory. Some formulation of quantum field theory uses temporary electron-positron pairs in its calculations called virtual particles. The mass, energy, and lifetime of these particles are related by the energy-time uncertainty relation. The energy of a quantum system is not known of a quantum systems is not known with enough precision to limit their behavior to a single simple history. Thus, the influence of all histories must be incorporated into quantum calculations, including those with much greater or much less energy than the mean of a measured / calculated energy distribution. The energy-time uncertainty principle does not temporarily violate The energy-time uncertainty principle does not temporarily violate conservation. The energy-time uncertainty principle does not temporarily violate conservation. The energy-time uncertainty principle does not temporarily violate the conservation of energy. It does not imply that energy can be borrowed from the universe as long as it is returned within a short amount of time. The energy of the universe is not an exactly known parameter at all times. When events transpire at very short time intervals, there is uncertainty in the energy of these events. The energy-time uncertainty principle does not temporarily violate conservation of energy. It does not imply that energy can be borrowed from the universe as long as it is returned within a short amount of time. The energy of the universe is not an exactly known parameter at all times. When events transpire at very short time intervals, there is uncertainty in the energy of these events. Harmonic analysis. In the context of harmonic analysis, the uncertainty principle implies that one cannot at the same time localize the value of a function and its Fourier transform. To wit, the following inequality holds: integral minus infinity x squared fx squared dx integral minus infinity c squared f hat x c squared d c greater equal f divided by 16p. Further, mathematical uncertainty equalities, including the above entropic uncertainty, hold between a function f and its Fourier transform f hat check hx plus hc greater equal log e divided by 2. Signal processing. In the context of time frequency analysis, uncertainty principles are referred to as the Gabor limit. After this, Gabor is sometimes In the context of time-frequency analysis, uncertainty principles are referred to as the Gabor limit, after Dennis Gabor, or sometimes the Heisenberg-Gabor limit. The basic result, which follows from Benedict's theorem below, is that a function cannot be both time-limited and band-limited. A function and its Fourier transform cannot both have bounded domains. See band-limited versus time-limited. More accurately, the time bandwidth or duration bandwidth product satisfies sigma t sigma f greater equal 1 divided by 4p approximated 0.08 cycles, where sigma t and sigma f are the approximating 0.08 cycles, where sigma t and sigma f are the standard deviations of the time and frequency energy concentrations respectively. The minimum is attained for a Gaussian-shaped pulse Gabor wavelet for the unsquared Gaussian EA signal amplitude and its unsquared Fourier transform magnitude sigma 2. The minimum is attained for a Gaussian-shaped pulse Gabor wavelet for the unsquared Gaussian EA signal amplitude and its unsquared Fourier transform magnitude sigma t sigma f equals 1 divided by 2p. Squaring reduces each sigma by a factor √2. Another common measure is the product of the time and frequency full width at half maximum of power divided by energy, which for the Gaussian equals 2 natural logarithm 2 divided by p, approximating 0.44. See bandwidth limited pulse. Stated differentially, one cannot simultaneously sharply localize a signal f in both the time domain and frequency domain. When applied to filters, the result implies that one cannot simultaneously achieve a high temporal resolution and high-frequency resolution at the same time. A concrete example of a resolution issues of a short-time Fourier transform. If one uses a wide window, one achieves good frequency resolution at the cost of temporal resolution, while a narrow window has the opposite trade-off. Alternate theorems give more precise quantitative results, and in time-frequency analysis, rather than interpreting the one-dimensional time and frequency domains separately, one instead interprets the limit as a lower limit on the support of a function in the two-dimensional time-frequency plane. In practice, the Gabor limit limits the simultaneous time-frequency resolution one can achieve without interference. It is possible to achieve higher resolution, but at the cost of different components of a signal interfering with each other. As a result, in order to analyze signals where the transients are important, the wavelet transform is often used instead of the Fourier. Transients are important, the wavelet transform is often used instead of the Fourier. Discrete Fourier transform. Let xn equal x0, x1, xn minus 1 be a sequence of n complex numbers, and xk, x0, x1, xn minus 1 be a discrete Fourier transform. Denote by x0 the number of non-zero elements of the time sequence, x0, xn minus 1, and bx0 the number of non-zero elements of the frequency sequence, x0, x2, xn minus 1. Then x0, majuscule x0 greater equal n. This inequality is sharp if equality achieved when x or majuscule x is a Dirac mass. More generally, when x is a non-zero multiple of a Dirac comp supported on a subgroup of an integers modulo n, in which case majuscule s this inequality is sharp with the equality achieved when x or majuscule x is a Dirac mask. This inequality is sharp with equality achieved when x or majuscule x is a Dirac mass, or more generally when x is a non-zero multiple of a Dirac comp supported on a subgroup of the integers modulo n, in which case majuscule x is also a Dirac comp supported on a complementary subgroup, and vice versa. More generally, if t and w are subsets of the integers modulo n, let lt r w l squared integers n divided by n integers L squared integers divided by n integers denote the time limiting operator and band limiting operators respectively, when LT RW squared smaller equal TW divided by G, where the norm is the operator norm of the operators on the Hilbert space. L squared integers divided by n integers of functions on the integers modulo n, and this inequality has implications for signal reconstruction. When n is a prime number, a stronger inequality holds. X0 plus minuscule x0 greater equal n plus 1 is covered by Terence Tau. This inequality is also sharp. Benedict's theorem. Amrein-Berthia and Benedict's theorem intuitively says that the set of points where f is non-zero and the set of points where f hat check is non-zero cannot be both small. Specifically, it is impossible for a function f in L squared R and its Fourier transform f hat check to both be supported on sets of finite Lebesgue measure. A more quantitative version is f L squared R d smaller equal c e c s sigma f L squared s c plus f hat check L squared sigma to the power of c. One expects that the factor ce to the power of cs sigma may be replaced by ce to the power of cs sigma to the power of 1 divided by d, which is only known if either s or sigma are convex. Hardy's uncertainty principle. The mathematician G.H. Hardy formulated the following uncertainty principle: it is not possible for f and f hat check to both be very rapidly decreasing. Specifically, if f in L squared R is such that fx smaller equals c1 plus x to the power of ne to the power of minus ap x squared, and if f hat check c smaller equals c1 plus c to the power of ne to the power of minus bp c f hat check fx smaller equals c1 plus x to the power of ne to the power of minus a p x squared, f hat check c smaller equals c1 plus c to the power of ne to the power of minus bp c squared, x greater than 0 n an integer. Then if ab greater than 1 f equals 0, while if ab equals 1 then it has polynomial p of degree smaller equal n, such that fx equals pxe to the power of minus ap n squared, x squared. Fx equals pxe to the power of minus ap x squared. This was later improved as follows: if f is an element of set L squared Rd is such that integral Rd fx f hat check x integral Rd fx f hat check c ep integral Rd fx and f hat check c e to the power of px c divided by 1 plus x plus c to the power of n dx dx smaller than fx equals px e to the power of minus p axx, where p is a polynomial of degree n minus d divided by 2, and a is a real d times d positive definite matrix. This result was stated in Berling's complete works without proof and proved in Hermander the case d equals 1, n equals 0. And Bonami, Dimench, and Yaming for the general case. Note that Hermander Berling's version implies the case AB greater than 1 in Hardy's theorem, where the H.G. Hardy's theorem, where the version by Bonami, Dimench, Jamie covers the full strength of Hardy's theorem. A different proof of Berling's theorem based on Liouville's theorem appeared in Reeve. A different proof of Berling's theorem based on Liouville's theorem appeared in Reeve. A full description of the case AB smaller than 1 as well as the following extension to Schwarz class distributions appears in Ref. Theorem of the temporal distribution F is an element of set S prime Rd is such that e to the power of px squared f is an element of set S prime Rd, and e to the power of px squared f hat check is an element of set S prime Rd, then fx equals px e to the power of minus paxx for some convenient polynomial p and real positive definite matrix A of type d times d. Additional uncertainty relation. Heisenberg limit in quantum metrology and especially interferometry. The Heisenberg limit is the optimal rate at which accuracy of a measurement can scale with the energy used in the measurement. Typically, this is the measurement of a phase applied to one arm of a beam splitter, and the energy is given by the number of photons used in an interferometer. Although some claim to have broken the Heisenberg limit, this reflects disagreement on the definition of a scaling resource. Suitably defined, the Heisenberg limit is a consequence of the basic principles of quantum mechanics and cannot be beaten. Although the weak Heisenberg limit can be beaten, systematic and statistical errors, inequalities above focus on the statistical impression. Systematic and statistical errors, inequalities above focus on the statistical imprecision of observables as quantified by the standard deviation sigma. Heisenberg's original version, however, was dealing with a systematic error at disturbance of a quantum system produced by the measuring apparatus, e.e. an observer effect. If we let epsilon A represent the error, e.e. inaccuracy of a measurement of an observable A, and eta B, the disturbance produced. If we let epsilon A represent the error, i.e. inaccuracy of a measurement of an observable A, and eta B, the disturbance produced of an. If we let epsilon A represent the error, i.e. inaccuracy of a measurement of an observable A, and eta B, the disturbance produced on a subsequent measurement of a conjugate variable B by the form of the measurement of A, then the inequality proposed by Masanao or Otsawa, encompassing both systematic and statistical errors, holds. Epsilon A eta B plus epsilon A sigma B plus sigma A eta B greater equal half A hat check B hat check. Masanao Otsawa. Heisenberg's uncertainty principle as general. Heisenberg's uncertainty. Masanao Otsawa. Heisenberg's uncertainty principle, as originally described in the 1927 formulation, mentions only the first terms of Otsawa inequality regarding the systematic error, using the notation above to describe the error disturbance effect of sequential measurement first A then B. It could be written as epsilon A eta B greater equal half A hat check B hat check. The formal derivation of the Heisenberg relation is possible, but far from intuitive. It was not proposed by Heisenberg, but formulated in a mathematical, consistent way only recently. As also, it must be stressed that the Heisenberg formulation is not taken into account the intrinsic statistical errors sigma A and sigma B. There is increasing experimental evidence that the total quantum uncertainty cannot be described by the Heisenberg term alone, but it requires the presence of all three terms of Otsawa inequality. Masanao Otsawa's equality. Masanao Otsawa. Using the same formalism, it is also possible to introduce. Using the same formalism is also possible to introduce the other kind of physical situation often confused with the previous one, namely the case of simultaneous measurements A and B at the same time. Epsilon A, epsilon B greater equal half A hat check B hat check. The two simultaneous measurements on A and B are necessarily unsharp or weak. It is also possible to derive an uncertainty relation that, as the Otsawa's one, combines both the statistical and systematic error components, but keeps a form very close to a Heisenberg original inequality by adding Robertson sigma A sigma B greater equal half A hat check B hat check. And Otsawa relations, we obtain epsilon A eta B plus epsilon A sigma B plus sigma A eta B plus sigma A sigma B greater equal A hat check B hat check. The four terms can be written as epsilon A plus sigma A eta B plus sigma B greater equal A hat check B hat check, defining epsilon vinculum A identical epsilon A plus sigma A as the inaccuracy in the measurement values of a variable A, and eta vinculum B identical eta B plus sigma B as the resulting fluctuation in the conjugate variable B. As the resulting fluctuation in the conjugate variable B causal Fuikawa established an uncertainty relation similar to the Heisenberg original one, but valid both for systematic and statistical hours. Epsilon vinculum A eta vinculum B greater equal A head check B head check quantum entropic uncertainty principle. For many distributions, the standard deviation is not a particularly natural way of quantifying the structure. For example, uncertainty relations in which one of the observables is an angle has little physical meaningful fluctuations later than one period. Other examples include highly B-model distributions or unimodal distributions with divergent variance. Quantum entropic uncertainty principle. For many distributions, the standard deviation is not a particularly natural way of quantifying the structure. For example, uncertainty relations in which one of the observables is an angle has little physical meaningful fluctuations larger than one period. Other examples include highly B-model distributions or unimodal distributions with divergent variance. A solution that overcomes these issues is an uncertainty based on entropic uncertainty instead of a product of variances. Well formulated in the many words interpretations of quantum mechanics in 1957, Hugh Everett free conjecture, a stronger extension of the uncertainty principle based on entropic certainty. This conjecture also studied by Hirschman. This conjecture also studied by Hirschman and proven in 1965 by W. Beckner and by Ivo Bialinski, Birula, and Jesse Michalski is that for two normalized dimensionless Fourier transform pairs Fa and Gb, where Fa equals integral minus infinity Gbe to the power of 2 PEAB dB and GB equals integral minus infinity FA e to the power of minus 2 BEEAB dA. FA equals integral minus infinity GBE to the power of 2 BEAB dB and GB equals integral minus infinity FA e to the power of minus 2 BIAB dB. Fa equals integral minus infinity GBE to the power of 2 PIAB dB and GB equals integral minus infinity Fa e to the power of minus 2 PIAB dAB. Ja, die. Da ist ein GB statt. Da hat ein GB statt FA. Fa equals integral minus infinity Fa Fa equals integral minus infinity GB e to the power of, ja klar, Fa equals integral minus infinity GB e to the power of 2 PIAB dB. A Fx Fb GB equals Fa 2 to the power of PIAB dA. The Shannon information entropies HA equals minus infinity. What? HA equals minus integral minus infinity Fa squared logarithm Fa squared dA and HB equals minus infinity integral minus infinity GB squared log GB squared dB are subject to the following constraint: HA plus HB greater equal logarithm E divided by 2, where the logarithms may be in any base. The probability distribution functions associated with the position wave function Gx and the momentum wave function Vx have dimensions Vc and the momentum wave function Vc have dimensions of inverse length and momentum respectively, but the entropies may be rendered dimensionless by Hx equals minus integral Gx squared natural logarithm x0 Gx squared dx equals minus natural logarithm x0 Gx squared HP equals minus integral Vp squared natural logarithm P0 Vp squared dp equals minus natural logarithm P0 Vp squared, where G0 and P, where X0 and P0, Gx, Px, Gx, Vx, where x0 and px are some arbitrarily chosen length and momentum respectively, which whenever arguments of a lower dimensionless. Note that the entropies will be function of these chosen parameters due to the Fourier transform relation between the position wave function Gx, the momentum wave function Vp. The above constraint can be written for the corresponding entropies as hx plus hp greater equal logarithm h divided by 2x0 p0, where h is the Planck constant. Depending on one's choice of the x0 p0 product, the expression may be written in many ways. If x0 p0 is chosen to be h, then hx plus hp greater equal logarithm e divided by 2. If instead x0 p0 is chosen to be h, then hx plus hp greater equal logarithm ep. If x0 and p0 are chosen to be unity in whatever system of units are being used, then hx plus hp greater equal logarithm eh divided by 2, where h is interpreted as dimensionless number equal to the value of a Planck constant of a chosen system of units. Note that these inequalities can be extended to multimode. Quantum states or wave function in more than one spatial dimension. The quantum entropic uncertainty principle is more restrictive than the Heisenberg uncertainty principle for the inverse logarithmic Sobolev inequalities. Hx smaller equal half logarithm 2 ep sigma 2x divided by x20 hp smaller equal logarithm 2 ep sigma 2p divided by p20 equivalently from the fact that normal distributions maximize the entropy of all such with a given variance. It really follows that this entropic uncertainty principle is stronger than the one used on standard deviations, because sigma x sigma p greater equal h divided by 2x hx plus hp minus logarithm e h divided by 2x0 p0 greater equal h divided by 2. In other words, the Heisenberg uncertainty principle is a consequence of a quantum entropic uncertainty principle, but not vice versa. I have a few remarks on these inequalities. First, the choice of base E is a matter of popular convention in physics. The logarithm can alternatively be in any base, provided that it be consistent on both sides of an inequality. Second, we call the Shannon entropy has been used, not the quantum von Neumann entropy. Shannon entropy von Neumann entropy. Shannon entropy von Neumann entropy. Finally, the normal distribution saturates. When inequality n is the only distribution with this property, because it is the maximum entropy probability distribution among those with fixed variance. Cf. here for proof. Entropic uncertainty of the normal distribution we demonstrate this method on the ground state of QHO, which is discussed above, saturates the usual uncertainty based on standard deviation. The limit scale can be set to whatever is convenient, so I assign x0 equals root h divided by 2m minuscule omega, gx equals m minuscule omega divided by ph to the power of 1 divided by 4, x minus m minuscule omega x squared divided by 2h equals 1 divided by 2px 20 to the power of 1 divided by 4x minus x squared divided by 4x 20. The probability distribution is the normal distribution. Gx squared equals 1 divided by x0 root 2px minus x squared divided by 2x0 2. With Shannon, gx squared equals 1 divided by x0 root 2px minus x squared divided by 2x20. With Shannon entropy, hx equals minus integral gx squared natural logarithm gx squared x0 dx equals minus 1 divided by x0 root 2p integral minus infinity x minus x squared divided by 2x20 natural logarithm 1 divided by root 2p x minus x squared divided by 2x to 0 dx equals 1 divided by root 2p integral minus infinity x minus u squared divided by 2 natural logarithm root 2p plus u squared divided by 2 du equals natural logarithm root 2p plus half. A completely analogous calculation proceeds for the momentum distribution, choosing a standard momentum of p0 equals h divided by x0, phi p equals 2x to 0 divided by ph2 to the power of 1 divided by 4 x minus x to 0 p squared divided by h2 phi p divided by phi p squared equals root 2x to 0 divided by ph squared x minus 2x0 to p squared divided by h squared hp equals minus integral phi p squared natural logarithm phi p squared h divided by x0 dp equals minus root 2x to 0 divided by ph squared integral minus infinity x minus 2x to 0 p squared divided by h2 natural logarithm root 2 divided by p x minus 2x to 0 p squared divided by h squared dp equals root 2 divided by p integral minus infinity x minus 2 p squared natural logarithm root p divided by 2 plus 2v squared dv equals natural logarithm root p divided by 2 plus half, where two big uncertainty is therefore the limiting value. Hx plus hp equals natural logarithm root 2p plus half plus natural logarithm root p divided by 2 plus 1 half equals 1 plus natural logarithm p equals natural logarithm ep. A measurement apparatus will have a finite resolution set by the discretion of its possible outputs into bins with a probability of lying within one of the bins given by the bond, where we will consider the most common experimental situation in which the bins are of uniform size. Let delta x be a measure of the spatial resolutions. We'll take the 0th bin to be centered near the origin with possibly some small constant of set c. The probability of lying within the jth interval of width delta x is pxj equals integral g plus 1 divided by 2 delta x minus c g minus 1 divided by 2 delta x minus c g x squared dx. To account for this discretization, we can define this Shannon entropy of a wave function for a given measurement apparatus as hx equals minus sum j equals minus infinity p xj natural logarithm p xj.